Okay, let's go ahead and talk about something called, they're closed intervals, and this will lead us nicely into the extreme value theorem. Okay, there's another value theorem coming. So let's talk about closed interval, because this is funky and it drives me crazy. Max and mins. Okay, so let's take a function, just for giggles. I don't know. I'm not even going to name the function except call it f of x. And let's go and whew. All right, let's do that. And I'm going to close this thing off. Let's close it off right here. And then I'm going to close this guy off right here. All right? All right, so this is A. We're going to close it off from A to B. It's a continuous function from A to B. All right, I'll name it f of x. Let's change color so we can start labeling stuff. All right, so check this out. This, first and foremost, easy to see, right? This is my abs max. Right? Now, you got to be a little bit careful with these, and we'll get into this again. Hopefully you saw all of this in Algebra 2. Remember, there is a difference between what is the maximum value and where is the maximum value. So if I think of this as being A, f of A, this is, again, just an Algebra 2 topic, but it's not a bad thing to revisit. A is where it is. F of A is what it is. So be really careful, okay? This right here is a rel min. If that's the absolute max, this guy, since it's not the same value, is going to be a relative max. And then this, of course, is going to be a relative min. Now you may say, wait, Ripley, why is that a relative min? It's lower than this guy. Yeah, but this guy wins. Now, this drives me nuts. First and foremost, we know for sure that this is the abs min, right? It is the absolute lowest that the thing gets. It's on the endpoint of the closed interval. It's on it's sitting here on the end. So it is allowed to be a min. Now, this right here, this is the one, I'm even going to draw a frowny face. Bleh, hate it. Now, in my brain, this should be a relative max, all right? This should be a rel max. And the reason why is it's bigger. Since, think of this as looking through a set of binoculars, and this is all that we can see. This thing right here is bigger than all of the values relatively close to it. However, again, remember, we make sort of these Faustian bargains in mathematics. We try to stay out of our way the most. We end up falling over ourselves often, but we try to stay out of our way the most. The problem is, because this is on the end of the interval, I can't open up a traditionally open interval in the set theoretic sense. So we say, no dice. It's not a relative max. It is neither. So unless it's an absolute max, and you may say, well, wait, Ripley, if it's the absolute max, how do I define? Yeah. The problem is, or excuse me, this is the absolute min, right? This is definitely the smallest of all the values. Nobody can argue with that. We don't need to open up an open interval to talk about this being an absolute min, because it's the smallest that it gets. However, this right here, I can't open up an open interval. And really, in the truest definition of relative maxes, you got to open up an open interval. So this one can't be. For an absolute max, who cares? It's the biggest or it's the smallest or whatever. Who cares for an absolute max or an absolute min? Okay, now that leads us ever so, not gently, into what's called the extreme value theorem. Now remember back, I think it was the last chapter, we talked about the intermediate value theorem. All of the value theorems, extreme value theorem, maybe a little tune there, EVT, sometimes you'll see this. Remember the intermediate value theorem was if I've got a continuous function from A to B, the function passes through all of the values between any 2 points. All right, the extreme value theorem starts the same way. All right, it says, suppose that f of x is a continuous function on a closed interval from A to B. That's how all of the value theorems start out. All right, continuous function, closed interval. Okay, if it's continuous, think about that. It means you can't lift your pencil. Okay, this implies that f of x must have, whoa, my pen locked up, must have both an abs max, whoa, sorry guys, getting a little crazy with this stylus today, both an, where am I, an abs max and an abs min for some, let's call it, I already used A and B, for some C and D, which are elements of the closed interval from A to B. Now that makes sense. I mean, think about it. If I've got, notice this was a continuous function. If I've got a continuous function, no jumps, no skips, no asymptotes, none of that crazy stuff, it's got to hit a max and it's got to hit a min for some value between A and B. In this case, this value right here, A, is really kind of our C from this guy, right? And then this is our D. This is where I hit my max. Now, let's explain. It's real easy to see why if the function isn't continuous, all bets are off, right? Take, for example, y equals 1 over x. All right, badly drawn. So if I do y equals 1 over x, and I close the interval from, I don't know, -3 to 3, show me where the absolute max is. Show me where the absolute min is. Well, the problem is this guy heads to negative infinity, so negative infinity wins. There's nothing more minimal than that. And similarly, this guy heads to positive infinity. But Ripley, you may say, why can't this guy be a relative min? Although, remember, the extreme value theorem talks about absolute maxes. But let's make sure we reinforce this. This can't even be a relative min because, remember, I can't crack open an open interval around it. So there are no maxes or mins for f of x equals 1 over x on the closed interval from -1 to 3. And the reason is this guy is discontinuous. Okay? All right, cool. Outstanding. All right, let's talk about a couple other things. Just a couple of quick theorems to get you through the section. All right, let's talk about Fermat's. You remember Fermat's last theorem? Well, strangely enough, he came up, whoops, this isn't his last theorem. This is just one of his theorems. Okay? All right. Now, let's think about this. What he says is, if f of x has a max or a min at f of c, okay? And remember, I could write suppose if I wanted to. Suppose and if are basically the same thing. So it's the p part of the p implies q, okay? And f primed of c exists. Now that's a biggie. Now think about that. If the derivative of f at c exists and the function has a max or a min at c, what has to happen at c? What's going to happen? Well, here comes the function. Okay, it has a max or a min. What's it got to do? It's got to level off. It has no choice. All right? That implies that f primed of c has to equal 0. If it's going to level off, then the first derivative equals 0. Now, why is this f primed of c exists so important? Well, because I can have a max or a min where f primed of c doesn't exist, right? It's a cusp, right? No dice. So I'm allowed to have that, but if the first derivative does exist, then it has to level off and it has to equal 0. But notice, we're saying suppose that it has the max or the min and f primed of c exists. So we got to be careful. We're not saying here that if the function has a max or min, then f primed of c equals 0. This is an example of where that doesn't happen, okay? All right, let's talk. I talked about this with you guys in Algebra 2 ad nauseum, but if you didn't have me, let's define critical points. Real easy, because these become really important. All right, critical points. It's extremely simple. A critical point, now we say critical point, but it's really a critical value, so I'll put that parenthetically. Let's call that a critical value. All right? It's super simple. It's a value of x, let's say x equals a, such that f primed at a equals 0 Or, and this is a huge or, especially down the road, we can't forget about this. Or f prime of a does not exist. That's our definition. So this is a definition. And I'm going to say, what's a critical point? What's a critical point? What's a critical value? Over and over and over again. So pound it into your head. It's a critical point if the first derivative equals 0 or doesn't exist. Period. Now, why are those so, quote unquote, critical? Well, because if a function, let's just write this up. Let's call this a If a function is to have a max or a min, it has to happen at either a critical point, and I'll start labeling these as CPs, but not yet. Critical point or an endpoint of a closed interval, right? It has to. Now you may say, wait a sec, Ridley, you're going back on what you said earlier with the Fermat thingy-dingy. No. Look, this derivative right here at this, let's call this x equals a. Wait, I should call it x equals c because I got an f prime to c there, don't I? Let's call that x equals c. It doesn't exist. And we define critical points as saying it's a value where either the first derivative equals 0 or it doesn't exist. Okay? So that is supremely important. It's really, really important for us to know excuse me, what to do as far as looking for places for maxes and mins. So let me change this obnoxious pink color. All right, what's the moral of the story? Okay, so now we have a story moral. Easy. If I'm looking for a max or a min of a function, take the derivative. I used to have an instructor that said, when in doubt, take the derivative. Just take the derivative. And it's absolutely correct. If all else fails, if you're sitting there and you're like, I have no idea what to do next, take the derivative. All right? So take the derivative and look for CPs. Okay? i.e. set f prime equal to 0 and solve for values of x that make it equal 0 or not exist. That's the move. That's it in a nutshell. We're going to do a ton of these. I just wanted to give you the lecture materials here because we're going to do a bunch of these in class. I mean, that's all we're doing is problems in class. Okay? So, hope you enjoyed it. Hope it gave you a little bit of information. I'll see you tomorrow in class. Have a good